In this video, we're taking a look at the meaning of oxidation and reduction. So what is oxidation and reduction? At first, oxidation was viewed as the gain of an oxygen. So when any element combines with oxygen, that element was oxidized. So all combustion reactions, since they're combining with oxygen as they react, are oxidation reactions. But every single oxidation reaction has to be a combustion reaction, one that involves burning. Iron rusting is probably the most common oxidation reaction you know, and that is not a fast burning violent process. It's a much slower drawn out process. So the process in which bleach will whiten stains and kills bacteria is also one in which a substance is being oxidized, so it is an oxidation reaction. And within every oxidation reaction, there's also a reduction, the opposite of oxidation. So again, going back to the original ideas of oxidation, when a substance was to lose an oxygen, that substance was reduced. So a substance that gains an oxygen is oxidized, and a substance that loses an oxygen is reduced. And we also call this a redox reaction. And this works for almost every single situation of when something gains an oxygen, it's going to be oxidized, and when it loses that oxygen, it is reduced. However, nowadays, this works in many more situations than one that involves just oxygen. We actually look at how the electrons shift from one substance to another and how the charges of those substances change because of those shift of electrons. So it doesn't have to be oxygen included. But this theory works because, with the exception of fluorine, every time a substance combines with oxygen, oxygen being the second most electronegative substance, is going to then take the electrons, so our other substance will be oxidized, and therefore the oxygen be reduced, again with the exception of fluorine, fluorine being the only substance that is more electronegative than oxygen. So now we define oxidation as the complete or partial loss of electrons and also the gain of oxygen, because again, the exception of fluorine, when you combine with oxygen, you're going to lose your electrons, whether it be partially in a covalent bond or completely if it's an ionic bond. And then we look at the reduction as the complete or partial gain of electrons or the loss of an oxygen, because now you're going to have the opposite happening. You're going to be getting electrons, and therefore your charge will be going down. So redox reactions with ions are really easy, because when you have ions, you have a complete transfer of electrons. You have an actual charge that's being changed. When you give up electrons, you become positive, and you take on electrons, you become negative. So defining redox within an ionic reaction then makes it much more easy to figure out. So with magnesium and sulfur, where magnesium is going to be giving up electrons to sulfur, then we have a complete transfer of electrons, magnesium going from no charge to a positive 2 charge as it gives up its 2 electrons, and sulfur going from no charge to a negative 2 charge as it takes on 2 electrons. In both cases, again, getting them to a noble gas electron configuration. And so here we see that reaction of magnesium with its 2 valence electrons, sulfur with its 6 valence electrons, and magnesium transferring 2 electrons to sulfur, making a +2 charge, sulfur taking on 2 electrons, making a -2 charge. And we can take this reaction and we actually split it into 2 half reactions. The oxidation half, the magnesium giving up 2 electrons to then make a +2 ion, and the reduction half, sulfur taking on 2 electrons to then make a -2 charge to be reduced. And again, we can put those now back together for our regular reaction of magnesium plus sulfur, making magnesium sulfide, again where magnesium is going to be oxidized because it's going to be losing electrons, giving up electrons to sulfur, and sulfur is going to be reduced because it's gaining electrons, it's getting those electrons from magnesium. So again, looking at these electrons with ions, when you lose electrons, you are oxidized. When you gain electrons, you're reduced. Nice easy way to remember this is Leo the lion goes gur. Lose electrons oxidized, gain electrons reduced. And so within that, and we also have a reducing agent and an oxidizing agent. The substance that does the reducing is the reducing agent. So in that case, magnesium was reducing down the sulfur because it was giving electrons to the sulfur. So our magnesium was the reducing agent. And then our sulfur was allowing magnesium to be oxidized. It was helping magnesium gain charge because it was taking those electrons. So sulfur was our oxidizing agent. When you have redox reactions with covalent compounds, it gets a little bit trickier because you don't have the shift of electrons. You're not actually gaining and losing electrons because you're going to be sharing them. So we kind of look at them in terms of if somebody were to get those electrons, though, who would be getting them. So here with hydrogen and oxygen, Again, we go back to our original definition of, well, the hydrogen is gaining oxygen, so hydrogen is being oxidized, therefore the oxygen must be getting reduced. And again, it's a very covalent bond, so actually we can almost look at it in terms of oxygen's getting electrons because it's pulling more tightly on those electrons than the hydrogen when they are sharing them, because it's a very polar covalent bond. Again, that unequal sharing gives hydrogen a positive charge and oxygen a negative charge. So with the gain and loss of oxygen, we also look at oxidation in terms of hydrogen, because as we see here, hydrogen is always going to allow the other substance to be reduced when you have a covalent bond. Because of the nonmetals, hydrogen has the lowest electronegativity. So anytime they're going to be sharing electrons, hydrogen is always going to lose that battle of electrons. The electrons will be held more closely tightly to whichever other nonmetal it is sharing electrons with. So again, oxygen being the second most electronegative, this is a very covalent bond. But even with something such as sulfur, which isn't nearly as electronegative as oxygen, it is still much more electronegative than hydrogen. So the electrons will be held much more closely to the sulfur than they would to the hydrogen. So when somebody combines with hydrogen, that will allow that substance to be reduced, and hydrogen will always be oxidized within, again, a covalent bond. So the most common kind of example of redox reactions is within corrosion. Think of steel and how it's made up mostly of iron, and iron is oxidized by oxygen to make rust, iron 3 oxide. And when iron is in the presence of compounds that have hydroxide containing compounds, and also in the presence of oxygen and water, it gets oxidized very quickly. Also within the presence of salts and acids, because they have those electrolytes, those positive and negative charges, it allows corrosion again to happen much more quickly. So iron, again, sitting in water, will oxidize much faster than an iron that's just exposed to the oxygen that's in the air. However, we know steel is an important substance in order for us to build these large infrastructures that we have, whether it be bridges or buildings. We need to be able to use that steel, use that iron. So we need to find ways to prevent that iron from corroding. So one way in which we do that is using these noble metals. Gold and platinum are not very reactive. They're not very willing to give up their electrons. So when we coat things with platinum and gold, it now protects that metal because of that outer coating that isn't likely to react. So some metals will lose their electrons very easily, again, making it really easy to then protect. So aluminum will give up electrons quite easily. However, unlike that of iron, when aluminum oxidizes and makes aluminum oxide, it isn't as brittle as rust, that iron 3 oxide. So aluminum oxide actually now makes a protective coating, and therefore now again protects that iron that's underneath. Iron, because when it oxidizes and turns to rust, is brittle and flakes away. New iron is exposed, allowing now more oxidation to occur. But when you coat it with aluminum, that aluminum oxidizes and it doesn't just flake away, doesn't just brush off like rust does, then it gives it protective coating, preventing any more oxidation to occur. So being able to control this corrosion is going to be really important, because we can't just replace the steel that's already within that infrastructure. You can't just pull out a beam and put a new one back in. So we got to find good ways of controlling this. Again, looking at how we can coat it with another metal, such as that is gold and platinum, which kind of gets expensive. So we actually will coat it in another nice metal like zinc. When you galvanize your steel, you put zinc on the outside again, because zinc will oxidize. It is a slow reaction, but also when zinc oxidizes, it doesn't flake away just like that of the aluminum. Another way in which you do it is coating with oil, because again, oil prevents water from getting in, and water really makes those reactions go much more faster. Same thing with paint in plastic, again, because now you're going to have an outer layer protecting the steel that's underneath, or whichever metal you're trying to protect that's underneath from being able to be oxidized. And another way is to then use what we call a sacrificial metal. So ones that, again, like zinc, like to give up their electrons and therefore are more willing to give up their electrons than the iron, which we're trying to protect. So we'll let those other metals, zinc and magnesium, gladly give up their electrons and become oxidized, and then allow the iron to not be oxidized. So here we see, again, galvanized nails. So we take nails which are made of steel, because steel is really strong, but if I now use these nails that are made of steel and they're not protected and they begin to rust, not only does it make an ugly, gross, orangey brown mess, it also now makes those nails weaker And over time, those nails get weaker and weaker and weaker and eventually just break. So we take these nails and again, we coat them in zinc. So now that steel is protected by that zinc outside coating, which will again give up its electrons, but then leave this outermost protected layer. Another way we should do it again with sacrificial metals, here we see the hull of a ship. And these are all chunks of magnesium that are attached to the bottom of the ship. And so when this ship is sitting in water, especially if it's the ocean and it's salt water, so you have all those electrolytes in there again, well now magnesium will get oxidized instead of the boat, which is made up of steel. And again, the steel is also painted, helping also protect it. But that magnesium will now get oxidized, so the iron will be left alone because of how willing magnesium is to give up its electrons.